Hello, welcome to Video Notes 10, Polynomial Division and Complex Zeros. For these notes, we'll look at how we divide polynomials with long division, why we would need to do it, and how to interpret the remainder of a division problem. And then for advanced, on the second half of this notes, we're looking more at complex zeros and how those contribute to the factors in polynomials and how they can be used to build up polynomials as well. So I wanted to start off with just a basic division problem. If you haven't divided something in a long time with long division, it can be jog to the memory. So we're looking at 12 dividing 540, or 540 divided by 12. What is the largest multiple? So this is the question we're asking. What's the largest multiple of 12 that fits in 54? So we can't divide 5 by 12, so that's why we skip all the way to 54. So the largest multiple that fits in 54 of 12 is 48. So what do I multiply 12 by to get 48? That's 4. So that means I multiply now. So multiply 12 by 4. I get 48. And then I subtract. And I get 6. And then I've got 0 that I move down. And then I start the process over again. What's the largest multiple of 12 that fits in 60? And that's 5. And then to check to see that I don't have a remainder, I get 0. So no remainder here. Ooh, my color's changed. We have been refreshed on what dividing looks like. Now this little idea over here, what's the largest multiple that fits? That is the way we will look at polynomial division as well. So when we start dividing this polynomial, you might notice automatically that this can be divided using synthetic division, and I would definitely use synthetic division here, but I'm going to show you what it looks like as long division, just so you can kind of see some similarities here. So we're going to take x minus 4 and we're going to divide this cubic by x minus 4. Now, I also want to check to see that all of my numbers are lining up in standard form, which is in descending degree order. So that's true, and all of them are present. So I'm not missing a degree. I've got 3, 2, 1, 0 degrees. So I don't have to add any zeros or x variables in with a 0 coefficient, so that's nice. But if we carry this out, I want to ask the question, what do I multiply x by to get x cubed? And I'd have to multiply x by x squared. So that's what I would put in as the start of my answer. So x squared times x minus 4 is going to be x cubed, as it should be, minus 4x squared. And I know I have chosen the correct answer because the result, when I multiply x squared by x minus 4, is going to get rid of my x cubed polynomial, and I'll have a new x squared polynomial to divide. So when I subtract, I get 0 and then minus 8x squared, and then the rest of my polynomial. And then I'll repeat the same process. So what do I multiply x by to get negative 8x squared? That would be negative 8x, and I'm keeping everything in line. and then I multiply. I go, what's negative 8x times x? I get negative 8x squared plus 32x, and then I subtract, making sure to keep parentheses around my subtraction because I'm actually distributing this negative to each term. So this was negative 12 plus 4x squared. So in this second subtraction, I get 0, and then minus 7x plus 26. And then lastly, I am figuring out what do I multiply x by to get negative 7x. I get negative 7. Then I multiply, and I get negative 7x plus 28. And I'll subtract. So my subtraction becomes negative 2. So I do have a remainder here. This is part of my remainder. And the way we write remainders with polynomials is we put them next to our last term, but we still are dividing them by x minus 4. So that's how our remainder is written. And that's our answer as well. If we wanted to check to see if we did it right, then we could multiply x minus 4 back through everything, and then we could find the initial polynomial, but that's the ticket there. And then here in number 2, I want to do this one with a binomial that is our divisor. So 6x minus 2 is dividing 6x squared plus 16x minus 1. And then I ask the question, what do I need to multiply 6x by to get 6x squared? I need to multiply that by just x. So I'm going to put my x on top of that ordered column. So I've got 6x squared minus 2x. Okay. Subtract that. Plus 18x minus 1. Then I've got, what do I need to multiply 6x by to get 18x? I need to multiply it by 3. Get 18x minus 6, and then I'm subtracting. So this is 0 plus 5, and then 5 is my remainder, plus 5 over 6x minus 2. So that's my result right there. Right. And then lastly, we have just a larger case where we're dividing a quartic by a quadratic. So I'm just being more careful to make sure everything is lined up with these. When we have more powers introduced into our polynomial, we'll have just more ways to kind of get out of order. So making sure that everything fits into the division bar, and then we write everything in the right column underneath each power is going to be really crucial. So here, same question, right? I take the leading term. It doesn't matter about these other ones right now. What do I need to multiply x squared by to get 8x to the 4th? And I need to multiply it by 8x squared. Now, if you haven't noticed already, sure, the first one was, you could use synthetic division for it. But on number 2 and especially 3, if you have a quadratic that you are dividing by, then you're definitely not going to want to use synthetic division. It's not possible with synthetic division, so we have to use long division. You'd have to factor x squared plus 3x plus 5, and that's not going to factor very nicely. In fact, it won't. You can find the zeros, but it's not going to be a big help for you in synthetic division, so we have to use long division. So 8x squared times x squared is going to give us 8x to the fourth. Great. We want that to cancel. And then plus 24x cubed. So I'm just multiplying. I'm just distributing my 8x squared to all the terms inside this quadratic. And then plus 40x squared. And then I subtract this whole polynomial. This ought to be 0. It is. This is minus 3x cubed, and then this is minus 13x squared. Let me double check that. So, yep, 24. Cool. So that means I start fresh with this cubic. And I'm looking for, what do I need to multiply x squared by to get negative 3x cubed? I need to multiply by negative 3x. So negative 3x cubed minus 9x squared minus 15x. Subtract all those. Thank goodness we're getting smaller numbers here, so 0, and then minus 4x squared, then minus 11x, minus 26. And then last time we have to play this game, we need to multiply by negative 4, so negative 4x squared, minus 12x, minus 20, subtract, and then we'll see what remainder we have. This is 0, this is x, and then this is minus 6. So our remainder is a binomial divided by that trinomial. Alright. So that concludes the lesson for honors. You guys are just looking at these division problems, being careful to keep everything in order. I did my best to line everything up. Here's where all the x terms are, here's where all the linear terms are, here's where all the quadratic terms were. I can't stress that enough. If you're organized with your work, then you can follow like what you did wrong, or you can double check someone else's work as well. Right. So that concludes the video for honors. At advanced, we've got to look at complex zeros occurring as conjugate pairs. And this might seem like it's a lot of information, but I really tried to pack it in as tightly but as efficiently as possible. So if you need to go back and look in the book, we are looking at page 173 in the pre-cal PDF. Or I should say in the book. I'm not quite sure what it is on the PDF. But if you need to go back and look at what I'm talking about, then you can go there and get maybe a more extensive bit of practice on it. But for complex numbers, we know that they can exist as a plus or minus bi, where a and b are integers, and then I is the imaginary number resulting from the operation of square root of -1. And these, like every number can be written as a complex number. Like 24 can just be 24 plus 0 times that imaginary number. So its imaginary component, which is that, is just 0. And we'll see cases where we have imaginary components that are 0, but we also will have an imaginary component. So the most common way we will use these in NTI for our pre-calc class is as a conjugate pair. And these conjugate pairs are seen as factors of polynomials, usually as sum or difference of squares. And sum or difference of squares happens so much that it's really important to know what a conjugate is. So with this first example, I've got two factors. They are conjugates because we have addition between the two terms and then subtraction between the same two terms. And conjugates are great because they force a difference of squares if a and b are real. I'll show you what I mean. So if I multiply these together, it shouldn't be a surprise as to what's going to happen. I'll get a squared x squared plus bax. Then I got minus bax if I, FOIL, distribute it properly. And then minus b squared. And then this will result as a squared x squared minus b squared. So this is just a difference of squares. So what could happen is if we know that we have a factor that has a conjugate, ooh, that highlighter is doing crazy things, then we know what its conjugate is, and we know how to find the resultant factor. And I'll explain what we mean as we go into our other examples. But here we have another set of factors where there is an imaginary component to the factor. So if I were to multiply these out, it would go a little something like this. We'd have a squared x squared, and then plus b a x I minus b a x I, and then minus b squared I squared. Now I know I squared is just square root of -1 squared. So this last term, well, these cancel out. Bye-bye. This last term is going to be -b squared times -1, which is just plus b squared. So with an imaginary component, we have a sum of squares. That's not really great because it doesn't tell us any real zeros, but we know how to find the factorization of such a polynomial if we could multiply it together or divide this factor out, for example. But let's go back to a little bit of the basics with these imaginary numbers and complex numbers and conjugate pairs, and look at just the x-intercepts of the quadratic found here. So I'm going to find the x-intercepts using the quadratic formula. So I'm going to take 3 minus the square root of 9 minus 4 times 1 times 4 over 2. And I should say have plus or minus there. When I find the 0 of this, I'll have -7 underneath the radical. And this is the traditional way you all have probably seen imaginary numbers presented to you. If I carry out with this work and turn my x-intercepts into and introduce that imaginary component into my x-intercepts here, then I'll have my complex 0 written out like this. So I have the a plus or minus b I format, which is how we write complex numbers. And like I said, everything can be written as a complex number. It's just we don't always have imaginary components. But in the case of this 0, we do have an imaginary component. And that comes from just writing out, show this a little bit more detail, writing out the square root of -1 times the square root of 7. And we know that that -1 is actually I. So I've just written it back here as being multiplied by square root of 7. All right, and then with number 5, we're diving a little bit more into this idea of conjugate pairs. And with x squared minus 6 times x plus 3 times x squared plus 8, we can determine its x-intercepts. That's not so hard. So we'll go throughout this whole thing. And figure out what the zeros are. It doesn't look very hard. And it's not. So I'll have 6 equals x squared, negative 3 equals x, negative 8 equals x squared. But then when I go to square root these things to really get into what these are, I end up with two solutions to these ones with the x squared in it. And I should get 2 zeros out of these. But when I take the square root of this one, plus or minus radical negative 8, I'll get an imaginary component to my complex number. So that's all fine, but what if I were going to like fully factor this out and show the conjugate pairs of like an even more detailed factored form of this polynomial? Then I would be able to write x minus radical 6 and x plus radical 6. Oh, would you look at that? There's our conjugate pair for that 0. I'll just do CP. This lonely factor in here, x plus 3, that doesn't have anything special. It's just a linear factor. Oh well. But then I can write another set of conjugate pair factors. Just by differentiating them by a minus and a plus. So I'm just showing you how factors can shake out with something that looks pretty easy. Just knowing that their factors can be written as conjugate pairs is pretty important. Because you might get a question like this. So a 0 exists at x equals radical 6. Sorry, radical 10. And we want to determine the factor related to this x-intercept. Okay, we'll just go ahead and do that. I know that factors of polynomials are written as the form x minus whatever their 0 is. So here we go. And it looks like we need to find the entire factor related to this x-intercept. Well, it looks like if this is supposed to be a conjugate pair, if this factor is supposed to have a conjugate pair, then its conjugate pair factor is radical 10. And the point I'm trying to make and drive home is that this factor, x minus radical 10, does not exist without its conjugate pair. If you have this 0, then you have its conjugate pair 0 as well. So they exist in tandem. And that's because what we found here before is we know that these zeros relate back to factors with x squared minus something or x squared plus something. So we know that these two factors, x minus radical 10 and x plus radical 10, relate to another factor that is in this polynomial. So we are going to go ahead and divide, we're going to go ahead and find that, that I guess, more complete factor that these two factors contribute to, just by multiplying them together. So I'm going to multiply x by x, so I get x squared. I don't really need to show this part since I kind of understand the pattern already. This is a difference of squares, so we know that the middle term should cancel out. It does. Lovely conjugate pairs. And then minus 10 is going to be how I multiply negative radical 10 and positive radical 10 together. So this is x squared minus 10. Wow, that looks pretty tame. That factor looks pretty tame. It was just kind of a trick to get to it. And to make sure that we get the full factorization of this polynomial that we're given, we'll just divide that out of the polynomial. Oops. So I'm going to do that real quick. So I need a 3x I'll skip, go all the way to negative 30x. Oh, look, they'll cancel out completely. So I'm left with x squared minus 10. Oh, all right. Well, cool. I just need to multiply everything by 1, and I'll get that, and everything cancels. Sweet. So there's no remainder. This polynomial is, in fact, divisible by x squared minus 10. You know that when we have a 0 as our remainder, that this polynomial is divisible, meaning it has clean zeros that come out of each factor, and that there's no remainder when dividing. All right, so the complete factorization for this polynomial, given this crazy setup, which isn't so crazy if we follow what we know about conjugate pairs, then we'll get this factorization. If you want to write maybe a more detailed factorization, then you can write out x minus radical 10, x plus radical 10. Either is acceptable, really. But it is much easier to divide this polynomial by the conjugate pairs multiplied together. So this x squared minus 10. So that's why we did that. All right, so that concludes our little extension to this. I'm sure there will be some questions, so look at the practice and see what your teacher has for you.